the first part of this video, we're going to talk about how to apply Newton's second law, the sum of forces is equal to the mass times the acceleration, when the acceleration is that of circular motion, specifically the centripetal acceleration, v squared over r. This comes from section 5.4 of your textbook. So say that the acceleration is equal to v squared over r. So we'll look at the case of a constant speed, circular motion, to keep the problems somewhat straightforward. Okay, so if we have constant speed, circular motion, right, then if we imagine the motion at any given point, the velocity, the direction of motion is tangent to that circle. And the acceleration, as we reviewed before, points towards the center of that circle. And so this was then what we called the radial acceleration, also called the centripetal acceleration. And so this centripetal acceleration always points inward. So what that allows us to do now, when we use Newton's law of the force equals the mass times the acceleration, the net force then also has to be towards the center of the circle. And so what you can say then is you can say that the sum of forces in the radial direction, since it's not an x or y direction per se, but actually points towards the center of the circle. So you can choose your axes so that one axis, say the radial axis, is along the direction of motion. The direction of the acceleration. And so the sum of the forces in the radial direction is going to be equal to the mass times the centripetal acceleration, which is then equal to mv squared over r. And so then this just adds an additional step to the problem-solving methods that we use for Newton's second law. That is that we're going to plug this in for the acceleration when we're solving the sum of forces equals mass times acceleration problems. So the best way to understand this is to just basically look at a couple examples. So as a first example, let's say that we have a car that's going to drive around a circular road. So a car is on a road, and we'll add in some friction to this. So let's say that the coefficient of static friction is equal to 0.600. Say that the radius of the turn that the car is going around is going to be equal to 35 meters. The question then is, what is the maximum speed that the car can go without slipping? So if you imagine this conceptually, then if you drive fast enough around a turn, the car is not going to be able to make that turn. The force of friction, which is static friction, even though the wheels are rolling then and moving relative to each other, the actual surface of the tire is not moving relative to the ground. There's no skidding motion. A skidding tire would be kinetic friction, a rolling tire is static friction. So if you turn too quickly, if you're moving too quickly during that turn, then the force of static friction isn't going to be enough to hold you on the turn, and the car is then going to skid, and its inertia takes over. So for this, we're going to assume what's called an unbanked road. You'll see often that on ramps or off ramps or in some area where people will be moving fast through a turn, that the actual road will be at an angle. And that angle then allows for not just the friction force, but also a component of the normal force to keep the car on the road. Okay, so we start like we always start, where we draw a Freebody diagram. Now for circular motion, you basically just pick one portion of the circle. Let's say we have a top view of our car, and our car is going to go around the road in this direction. Here's the center of the circle. So assume I'm looking from this direction at the car. I can draw the car like this. Here's the back of the car basically. Here would be my center of the circle over here, which means that that's going to be the direction of the acceleration. So what that tells me is that that has to be the direction of the force of static friction acting on the car, because that's what's keeping it going in a circle. That's what's causing it to have a centripetal acceleration. That's what's causing it to change its direction. If there wasn't enough static friction, or if there is no static friction, say in the case of ice, then you wouldn't have that force and you wouldn't be able to go in a circle. Alright, so here's the ground to orient ourselves, and so then that allows us to say that we have our other normal forces acting, our typical forces, which are the weight and the normal force. So I have then this free body diagram. I'm going to choose this. I'll call that my radial direction. I like to denote it by r hat, but you can denote it however you like. And then orthogonal to that, my standard vertical axes. Okay, so at this point then, I can look at the sum of forces in y and the sum of forces in x. Let's do the sum of forces in y first, because we note that in the y direction it's in mechanical equilibrium, so the sum of forces in y is equal to 0. So that then allows us to also say that the sum of forces in y, if we look at the individual forces, we have the normal force pointing up, we have the weight force, mg, pointing down, and then we can then set these equal to the mass times the acceleration. So again, you identify the individual forces acting, and then you set it equal to the mass times acceleration. And then you have your equation of motion for this. So we see very simply in this case, with no angles, no additional forces in the vertical direction, that n equals mg. Note, however, that that is of course not always the case. So don't always assume that the normal force equals the weight. Alright, we can now look at the force in the radial direction. So that would be the sum of forces in the radial direction. Well, the individual forces in the radial direction, there's only one, and it's going to be equal to that force of static friction. And in this problem, it's asking what is the maximum speed that the car can go without slipping, which means that what we want to examine is the case where the static friction is at a maximum, and then try to find the speed from that. So we want to know where the maximum static friction is, and then that's so basically we can solve for the maximum speed that will apply. Okay, so the force of static friction, that is what's acting, and it's the only one. So there's my sum of my individual forces. And now I'm going to be setting it equal to my mass times my acceleration, which I know then is equal to my mass times my speed squared divided by r. And what I'm going to write here is V max squared, since I'm using the maximum force of static friction. That's going to correspond to the maximum speed allowed. So now I can just go ahead and solve this. I can say F sub s max equals m V max squared over r, and we know that F sub s max is equal to mu sub s n. We've already solved for m, so that's going to be mu sub s times mg. So we can then use this relationship for F sub s max, put it into this relationship here. So we end up with that the mu sub s times mg equals m times V max squared over r. The mass cancels out, showing that actually this result is independent of the mass of the car, which is why often when you're driving you'll see a sign saying a recommended speed or caution, this is the speed you need for the turn, and it's not just for heavy cars or light cars, it's independent of the mass. And that's then because most coefficients of static friction are approximately the same for most cars, and so you end up with about the same maximum speed allowed for a given road. Okay, so then that allows us to solve for Vmax, and we say that Vmax here is going to be equal to the square root of mu sub s times r times g. So at this point we have our result, and we want to just put in our values that were provided in the problem. When you plug in those values and use your calculator to solve, you'll find that the maximum speed for these particular specifications is 14.3 meters per second. So now we're going to move on to another example, this time a conceptual example, that asks us at each instant shown, A, B, C, and D, to draw the free body diagram of the block, assuming that it's moving along these tracks at a constant speed. We're told to keep the weight arrow length the same in each diagram, right? Since the mass is not changing, the force of gravity is not changing. So then we would have identical lengths of weight arrows between all our diagrams. But we're told to adjust the length of the normal force appropriately. And the reason the normal force will change is because the direction of the acceleration is going to change in these different situations. So if we start with A, and we first note that it's going over the top of this circular path, which means that the acceleration in this situation is going to have to be downward. So the radial acceleration in this case is going to be down, which means that the net force is also downward in that situation. So our diagram, let's choose sort of average length for our weight arrow. Well, the normal force in this case, it's the ground and the car, it's the contact force between them. So it's going to have to be upward for this geometry. And we know that the net force has to be down because that's the direction of the radial acceleration. So now we know that we have to have some sort of smaller normal force arrow relative to our weight. For case B, in this case, the radial acceleration is upward, and so if we have this same weight arrow, we know that the net force has to be up because that's the direction of our centripetal acceleration. So that tells us then that our normal force has to be bigger than our weight. In case C, we have the bottom, and it's going to be moving around this turn. The centripetal acceleration at this point is towards the center of the circle, and so this situation is actually not different at all from B. So this is going to be exactly the same as situation B. The normal force is upward, the weight is down, and the normal force would have to be bigger than the weight. Now for case D, we would have the situation where the car is upside down, so now the track is above it. So imagine the contact force between the car and the track. Well, the contact force, the track, is actually going to be pushing down on the car. The car is pushing up on the track. So if we draw our diagram with our same weight force, and we recognize that the centripetal acceleration is towards the center of the circle, that means our net force is down, but our normal force is also down. So the normal force is also down. But in this case, we actually can't decide how it compares to the weight. So the normal force in this situation could be larger, smaller, or the same even as the weight. It really depends on the speed and the magnitude of that centripetal acceleration. All right, in our last example for circular motion, we're going to use the example of a ball that's swinging in a horizontal circle at a constant speed. And you're given the radius that it makes, along with the angle theta that the rope makes with the vertical axes. The question is, what's the speed of the ball in terms of r, theta, and g, the acceleration due to gravity? Okay, so in this situation, we want to start like we always do, which is to draw our free body diagram. And in this case, we really have two forces acting. We have the weight, which is mg, and then we have the tension and the rope. And the tension is what's causing the centripetal acceleration. So the tension goes along the direction of the rope, away from the object. And this angle, if this is theta, note that this is also theta here. So that then allows us to say that this is the angle that the tension makes with the vertical axis. Okay, so the direction of the center of the circle is over here. I always like to mark that so then I can choose my radial component, my radial axis, and my vertical axis. Now, if we go ahead and analyze this situation, we can again start with the y direction because we know it's an equilibrium in y. The sum of forces in y are 0. So if we now look at the individual forces that are acting in the y direction, well, we have two. First, we have this vertical component of the tension, right? So there's only the component of the tension that points vertically opposite of the weight. And we see that that component is actually adjacent to this angle theta. So we can write it as t times the cosine of theta because of this triangle here where we have our vertical component of the tension and the horizontal component of the tension. So the vertical component is t cosine theta, and it's positive y direction, and then minus mg because that is in the negative y direction. So then we equate the sum of the individual forces to the mass times acceleration, and so we can then see that t cosine theta is going to be equal to mg. So now we have one equation. Often you end up, as you've seen, with two equations and two variables. In this case, we have one equation which involves the tension in terms of known quantities for g and theta. We haven't been given information about the mass. And this is an example of how in problem solving you don't panic when you're not given information, and you just hope that if you follow it through, that information will cancel out. Okay, so in the radial direction, we can write the sum of the forces in the radial direction. Well, we only have one force there, and it's going to be the horizontal component, this radial component of the tension. So the radial component of the tension is going to be equal to t times the sine of theta because it's, again, opposite of this angle theta. And that's our only individual force acting in the radial direction. And then that's going to be equal to the mass times the acceleration in the radial direction, which is equal to m times v squared over r. And what we want is the speed. Now, before we go ahead and solve these equations for what we want, I'll note that just conceptually by looking at this, you can tell that the tension, the magnitude of the tension, has to be larger than the magnitude of the weight, because the vertical component of the tension has to equal the weight, and there's also the horizontal component of the tension. And so then the tension itself is made up of the vector sum of those two components, which then will always have to be larger than the weight. Okay, so now we have our two equations, and we can solve them for the speed. So we can set over here that the tension is going to be equal to mg divided by cosine theta. So we can say here that the tension is equal to mg divided by cosine theta from this first equation, and then we can put that into the second one here. So we can say mg divided by cosine theta times the sine of theta, is going to be equal to mv squared over r. And now we're happy because our masses cancel out, and so we can solve this equation for our speed, which is going to be that v is equal to the square root of r times g times the tangent of theta. So r, g, tangent theta. And then that is our result. In the last part of this video, we're going to discuss adding in air resistance and how it relates to the idea of terminal velocity. This shows up at the end of section 5.3 of your textbook. Alright, so air resistance is different from friction because air resistance depends on velocity. So air resistance will increase as the velocity of the object increases. So air resistance depends on the velocity, and that's a big difference than friction. So if we talk about the air resistance, which I'm going to call R just to be able to keep it straight, your book calls it little f, which is the same as used for friction. So I want to be clear that we're talking about air resistance. So the magnitude of the air resistance force, R, is going to depend on the speed of the object, v. And specifically, we can say that R is going to be proportional to v, directly proportional to the speed. And that's true for objects traveling at lower speeds. A common thing would be looking at an oil drop fall through water, and then it's almost exactly proportional to v. More commonly, when we observe air resistance as impacting something's rate of falling or moving, it's going to be moving at higher speeds. And then the force of air resistance is going to be proportional to the square of the speed. So this would be the typical relationship that applies to, say, a car driving down the highway, and also, say, skydivers, etc. Alright, so if we actually now look at what happens to a free body diagram of the object falling through the air. So let's say that we have a free body diagram of a falling object. And the object is no longer in so-called free fall because we're not ignoring air resistance any longer. So let's draw it at 3 separate times. So we have time 1, time 2, and time 3. Well, in all cases, the weight is the same. We would expect fully that the mass is the same, g is the same, so the force of gravity hasn't changed in any of these instances. However, let's say as it's getting faster and faster, so as it's falling, it's getting faster and faster. Let's say it starts off fairly slow, so it would have some relatively small force of air resistance acting. As it falls faster, that force gets larger, and then as it falls even faster, that force gets even larger, until at some point the force R equals the force of the weight. And in that situation, now all of a sudden you have no net force, which means that you're going to have a constant velocity, and your acceleration is down. So let's kind of talk about each of these situations, and we'll see the progression towards terminal velocity. So this one would be the slow example, where the sum of forces is downward. But note that the acceleration is not equal to g. The acceleration, the magnitude of the acceleration, is less than g. The equation that we would get is that mg minus r equals ma. This would still apply in this situation, where now it's flying, it's falling faster. The sum of forces is still downward, but now the acceleration is even smaller. Right? If we look at this one, we know that the r has gotten larger, so the acceleration is getting smaller. So the acceleration gets smaller and smaller as we go. And then we have this situation. It keeps increasing until so-called terminal velocity. And terminal velocity, R equals mg, which means that the sum of forces is equal to 0, so the acceleration equals 0, which is then how you end up with a constant velocity. So the constant velocity as it falls. So we can now say that terminal velocity is going to depend on the mass, which is why something like a feather hits terminal velocity very soon, something like a bowling ball does not. So the larger the mass, then the bigger the terminal velocity. So let's draw a small mass and let's draw a heavy mass. A heavy mass obviously has a larger mg. This one would have a very small mg. And so in order to reach terminal velocity, they would each need to have different values for their actual force from air resistance. And remember that R depends on the speed. So in order to get a bigger R, you need to have a faster speed. So this one then is going to have a larger speed, a larger terminal velocity, when R equals mg. Alright, so now we can actually talk about the equations of motion for an object that is experiencing air resistance. And if we look at these, we've already written down that mg minus r is equal to the mass times the acceleration. So what we can do is say that r is proportional to v, so the case of something falling slowly. In that case, it turns out that we can write that r, the vector r, is going to be equal to negative times a constant times the velocity vector, because it's always going to point opposite the velocity, right? It's a resistive force. K here is a constant. So what we can do then is talk about how, in this case, the magnitude of r, this here is the magnitude of r because I've already included that negative sign, is going to be equal to k times v, the magnitude of the speed. So here I can put in that mg minus kv equals the mass times acceleration. And so at first that might seem like an equation that has two variables in it. It's, say, you know the mass g and that constant. But it's actually not, and those that have had differential equations then will begin to recognize how you solve this. So I'm introducing you to the idea now, although you're not going to be expected to solve any differential equations in this class. So mg minus k times v is equal to the mass times the acceleration, but remember that the acceleration actually depends on the velocity. So that's the mass times dv dt. And so you actually now have velocity as a function of time as a result for this. So you can get velocity as a function of time by solving this so-called differential equation. And the reason it's a differential equation is because it's not our standard algebraic equation that has just constants, but instead now it involves the derivatives of some of the variables. All right, so the differential equation, if you actually do take differential equations eventually, then you'll learn that the solution to this particular one is exponential. So the solution here is exponential. And so you can actually then plot the velocity or the speed more as a function of time, and it's going to then rise exponentially and then taper off at the terminal velocity. So this here would be our terminal velocity. Once you know the velocity is a function of time, you can get the acceleration, and again I'll plot the magnitude of the acceleration as a function of time. And this is going to start initially at g, right, at 9.8 meters per second squared, and then it actually decreases exponentially to 0 down here. And these make conceptual sense. As something begins to fall, the air resistance increases, but it's still getting faster and faster. So it gets faster and faster and faster until it reaches terminal velocity. As the air resistance force grows, the actual net force decreases, which causes the acceleration to decrease all the way until terminal velocity. Alright, that concludes this portion of the required video. Again, contact me with any questions you have.